This is SpaceTime, Series 23, Episode 11. Coming up on SpaceTime, growing evidence for a second planet around Proxima Centauri. Discovery in Australia of the oldest dated asteroid impact crater on Earth. And could Saturn's moon Enceladus be habitable? All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers are finding growing signs of a possible second planet orbiting Proxima Centauri. A report in the journal Science Advances claims the new candidate exoplanet, which would be named Proxima C, has about 5.8 times the mass of the Earth and an orbital period of 5.21 Earth years, with a surface temperature of minus 234 degrees Celsius. Located just 4.23 light-years from Earth, Proxima Centauri is the nearest star to the Sun. It's part of the Alpha Centauri triple star system. The two primary stars, Alpha Centauri A and B, orbit each other around a common centre of gravity every 79.91 Earth years. Like the Sun, Alpha Centauri A is a spectral type G yellow dwarf star. It's about 10% more massive than the Sun and just over 1.5 times as luminous. Its binary partner, Alpha Centauri B, is a spectral type K orange dwarf star, a little smaller and cooler than the Sun, with about 90% of the Sun's mass and about half its luminosity. The third star in the system is Proxima Centauri. It orbits the other two stars at an average distance of about 0.21 light-years, about 430 times the size of Neptune's orbit around the Sun. Proxima Centauri is a spectral type M red dwarf star, with about 1/7 the diameter and 1/8 the mass of the Sun. In 2016, astronomers confirmed the existence of an Earth-sized terrestrial planet orbiting in the habitable zone around Proxima Centauri, making it the nearest known exoplanet to Earth. The planet, known as Proxima b, takes just 11.2 Earth days to complete each orbit around its host star. That's far closer than Mercury's 88 Earth day orbit around the Sun. But while it is orbiting awfully close to its star, the very fact that the star is a red dwarf, and therefore fairly cool, means Proxima b still orbits within the star's habitable zone, where temperatures would allow liquid water, essential for life as we know it, to pool on a planet's surface. Then in 2017, astronomers using the Atacama Large Millimeter Submillimeter Array Telescope in Chile reported the discovery of an unknown source about 240 million kilometres out from Proxima Centauri. That's just a little bit further away than Mars's orbit around the Sun. Then detailed studies by Mario De Masso and colleagues from the Torino Astrophysics Observatory, looking at 17 years' worth of radio velocity spectral data, detected a regular wobble in Proxima Centauri every 1900 Earth days. And that suggests it's being gravitationally influenced by an as-yet unseen orbiting planet. You're listening to SpaceTime. Still to come, the discovery of the oldest dated asteroid impact crater on Earth. And later in the science report, Australian researchers recreate the 2019 nCoV coronavirus in the laboratory. All that and more coming up on SpaceTime. Outback, Western Australia's Yarrabubba crater has set a new date record as being Earth's oldest discovered asteroid impact structure. The 70-kilometre wide feature is estimated to be some 2.229 billion years old, making it some 200 million years older than the next confirmed oldest impact structure, the Vredefort Dome in South Africa. The findings, reported in the journal Nature Communications, show that the impact date coincides with the end of a deep global freeze known as a snowball Earth. The snowball Earth hypothesis proposes that planet Earth has undergone several periods of almost, if not total, global glaciations. Snowball Earth events are extreme glaciations far more extensive than ice ages. These periods of icehouse climates resulted in the planet's surface being entirely or nearly entirely frozen over, with ice sheets up to 2 kilometres thick and average surface temperatures of minus 50 degrees Celsius. One of the study's authors, Professor Chris Kirkland from Curtin University, says the Yarrabubba crater has been recognised as an impact structure for nearly 2 decades, but its age hadn't been well determined. until now. Yarrabubba is about half the age of the Earth and situated in the Yilgarn Craton, one of the most ancient pieces of the planet's crust, located between Sandstone and Meekatharra in central Western Australia, northeast of Perth. The impact date was confirmed by a detailed analysis of the minerals zircon and monazite, which were found at the base of the eroded crater. These minerals had been shock recrystallized by the impact. The age of the Yarrabubba impact matches the end of a series of ancient snowball Earth events known as the Huronian glaciation. The geologic record shows that after this impact, glacial deposits were absent for the next 400 million years. Kirkland says the timing of the impact raises the possibility that this event may well have helped lift the planet out of its global deep freeze. Kirkland's calculations indicate that a 7-kilometre wide asteroid impacting into a 2-kilometre thick ice sheet at 17 kilometres per second could have sent over 500 billion tonnes of water vapour, an important greenhouse gas, into the atmosphere. And numerical modelling further supports the connection between the effects of large asteroid impacts into ice and global climate change. Kirkland says the findings suggest the impact may well have tipped the scales just enough to end glacial conditions.
We've recently determined the age of Yarrabubba impact structure in Western Australia. So that's a crater that lies Outback, WA. So it's right out in the bush. So if you were driving out there, you actually probably wouldn't recognise it's a crater. It's a very flat landscape, but with geophysical imaging, we can recognise a 70-kilometre diameter crater, and there's a distinctive rock right in the centre of that crater. So work that we've recently carried out at Curtin has determined an age for that impact structure at 2.2 billion years ago, so that's about half the age of the Earth, and it makes it the oldest recognised crater on the planet.
Could you determine what caused it? Was it an iron meteorite, or any ideas at all there? Any remnants for you to look at?
No, unfortunately not. So it's been completely, the impactor itself has been completely vaporised. Also, we've got to remember that we're now looking back into the really formative age of our planet. So the structure itself is very deeply eroded. So we're looking now down into the deep, deep roots of the impact structure itself. So a huge volume of material has been stripped off.
You were very lucky in that this was a really old piece of the Earth's crust that this impact occurred in. This is a surviving remnant of the very ancient Earth.
Yeah, that's exactly right. The area the impact has actually happened in is called the Yilgarn Craton. So that's an extremely old part of Western Australia. It's not the oldest part of WA, but it is an old part of WA. And it reflects a very old piece of continental crust. So that's the Belsic, so that's the light part of the craton that floats above oceanic crust and kicks around for a long time. It's mainly composed of granite, and it's actually a well-mineralized area. So there has been quite a lot of geological research in this area because it's an area that's prospective for gold mineralization, for example. So geologists do go out and look at this ancient area.
2.229 billion years old. That's ancient. That's even older than the people I went to school with. How do you determine the age?
Yeah, so 2.2 billion years ago, plus or minus 5 million years, half the age of our planet. Yeah, as geologists, we like to look at rocks, so we go out and chip a bit of the rock off, and we bring that back to the laboratory, and we crush it up. So now we've gone from a rock to something that looks like a pile of sand, and then that's when the hard work really starts. So we get out a pair of tweezers, and we start to sift through that pile of sand looking for very specific mineral grains. And the mineral grains we're after are grains that contain uranium within them. So that's minerals called zircon or monazite, for example. And those grains, because they contain uranium, it's very useful for us because through time, uranium changes to lead. Now, the neat thing about that is the rate of conversion from uranium to lead is actually quite well known. So that kind of decay rate is known. So if we're able to measure the amount of uranium and the amount of lead, we can calculate an age. So what happens whenever an impact event comes in, it comes in and these zircon grains are already there because they formed earlier in the history of the rock. But the impact event basically flushes out all the lead that was in those little grains. So that resets our clock. So then after the impact event, the uranium starts to accumulate lead again, and we then can determine both the age of the formation of the granite, but we can also determine when this major shock event known as shock metamorphism happened and basically reset our stopwatch at the time of impact.
And that gives you a really accurate age for this rock.
Yeah, that's right. Yeah. So it's cool that we can determine, not only the age of the impact event itself, but also the age of the primary magma that formed the granite in that area. So we're able to extract a huge amount of information. Basically, what it looks like, we have these little crystals. Those little crystals have more or less like tree rings, if you like. Some of the domains within the crystal are undisturbed or unshot, but around the edge of the grain, there is this really quite beautiful recrystallized area, which has basically been completely shock metamorphosed or completely changed and expunged all its lead. And those are the areas that we'd look at to get the age of impact.
And you really need a strong impact, like an asteroid event, to cause that recalibration, don't you? It doesn't happen by small events like a local earthquake or something like that. You need something.
That's exactly right. So we can tell that it's a major event from the change in the crystal structure, which we're also able to look at. So the crystal structure has been completely changed. But to just cause the expulsion of lead out of a crystal, we need to get to temperatures probably above 1,000 degrees and probably much, much above 1,000 degrees. So this is a really significant event to reheat the rock in that area to such an extent to cause it to recrystallize. We also form a range of other shock features in the rock that are very distinctive and indicative of shock metamorphism. And the only real way to do that is with a huge impact event. We can't do it with any real process within the Earth. So we have to appeal to extraterrestrial forces, like meteorite impacts. It's the only way to do it.
And the timing of this is rather interesting too, because the asteroid which caused this event struck the Earth at a time which just happens to coincide within 100 million years of what we regard as the end of the Huronian glaciation. This is one of the probably the first major snowball Earth events.
Yeah, that's spot on. You've got it exactly right. The Earth has had probably several snowball events, so globally frigid conditions. But Yarrabubba coincides right at the end of the first major kind of series of global or potentially global glaciation at 2.2 billion years ago. So right as that impact happened, we lose glaciations from the geological rock record for 400 million years. So there's no evidence of any glaciations after Yarrabubba, but prior to Yarrabubba, there is evidence of widespread, potentially global glaciation. So that starts to get us to think about, is this a major event that happened on Earth, and did it really change global climate and send our planet down a very different evolutionary pathway?
These snowball Earth events are really quite major changes in the planet. We don't really know what causes them, do we? We've got a whole bunch of theories, but this one we think may have had something to do with oxygenation of the planet.
Yeah, that's right. That's totally spot on. The other interesting thing is with the timing of Yarrabubba, it coincides when we start to see very distinctive, known as red bed rocks, start to develop in the rock record, and those appearance of red beds is another indication of, the development of an oxygen-rich atmosphere. So all these things seem to coincide and pivot around this Yarrabubba impact event, which is really very curious and gives us thoughts about maybe using a model to explain these global climate changes with the strong influence of an impact event.
And ironically, if you were to drive a few hundred miles, many hundred miles to the west of where you are at the impact site, you'd come across the stromatolites, which may well have been one of the primary causes for the oxygenation event.
Yeah, that's exactly right. So I think in Western Australia, we're very lucky. We've got this very rich geological record because parts of the crust here are so old. So we've got the potential of preserving many of these geological events in our rock record, which really is our only record into really deep time of our planet. Yeah.
The amazing thing is, of course, before this snowball Earth event, the Earth had a primarily methane atmosphere, and then the stromatolites began photosynthesizing the gases and making food out of sunlight, and as that happened, they released oxygen in the air, and that basically polluted the planet from the point of view of the life that was there beforehand, but at the same time, it created the world we have today.
Yeah, that's exactly right. So now in that picture you've just painted, we now need to place right in the middle of that this major impact event where potentially up to a 5 kilometer diameter impactor came into the planet, created a 70 kilometer wide impact structure. But if it hit continental ice, which is possible, it would have jetted up a huge volume of water vapor instantaneously. And that water vapor we know is a very good greenhouse gas. So this could be a major climate shift event by having an impactor going into thickened continental ice. So we ran some calculations, and the amount of water vapor that would be instantaneously liberated is quite phenomenal by impacting into a glacial ice sheet.
Around 500 billion tons, I believe.
Yeah, that's exactly right. So of course these are models, and we're basing them on the information we have. So we don't really know about the thickness of the ice sheet, and we have to use our kind of geophysical evidence about the size of the impact structure to try and back calculate out the size of the impactor. But all these pieces of the puzzle seem to be coming together and pointing towards Yarrabubba being a very significant event in our planet's history.
The replacement of the methane atmosphere with an oxygen atmosphere, that meant the Earth's atmosphere became really thin, and that allowed a lot of heat to escape, which is probably what triggered the snowball Earth event in the first place.
Yeah, that's right. So normally we think of the end of snowball events being caused by factors related to the planet itself, volcanism. So volcanism releasing ash. Ash might change planetary albedo, so the amount of reflectance, but also changing the atmospheric composition. But what's interesting, if we look at the 2.2 billion years ago, we seem to be in a period where there was little magnetism. It's been known as the geodynamic lull. That's what geologists like to call it, but basically a period when there wasn't much magnetism on our planet. So it makes it difficult to really appeal to volcanism to have brought Earth out of the first snowball event, which is why that's another pointer towards maybe Yarrabubba as an impact event had something significant to do with taking Earth out of this early snowball condition.
As things get colder and colder, they get whiter and whiter. Look at the Arctic and Antarctic. And so there's more reflectivity. The albedo of the planet changes, and so more of the heat from the sun is reflected back out into space. And so by having a huge event such as this, pumping as much water vapor into the atmosphere as it did, you then provide that warming blanket again for the planet, allowing it to warm up.
Yeah, that's exactly the model we're proposing. There is much more that can be done in terms of testing this geologically. One thing we would very much like to do is demonstrate that the impactor actually did come into a thickened volume of ice based on data from WA. We have indications from South Africa that there is these rocks called diamictites. Now, diamictites are kind of special rocks. They're rocks that are produced when glaciers bulldozer across the continents, and by bulldozering across the continents, they crush up rock, produce big blocks of rock, but also a very fine grained rocks, and all this material is jumbled up together. So these diamictites are what we use to determine when global glacial events occur. And as I mentioned, as soon as Yarrabubba happens, we basically lose from the rock record these diamictites. So it's pointing towards something very significant happening at this time.
Considering the Earth's orbit's changing, the tilt of the Earth changes, you guys are looking at evidence of glaciation at paleo-equatorial regions in order to determine what's an ice age and what's a snowball Earth event. Is that difficult to differentiate between all that?
Yeah, of course it is. So you're spot on. The challenge there is, just as you've alluded to, is how do we determine if a glacial event was at the poles, in which case, that's relatively normal, or was it at the equator? So one way of trying to determine that is to, again, go back into our rock record and look at the paleomagnetic properties of the rock and try and use that to understand if the glacial event was in the high Arctic or if it was down around the equator. Now, if it was down around the equator, again, that would be pointing towards globally frigid conditions. Whereas if it was just a high latitude event, then, we don't need to appeal to such inclement, if you like, conditions.
Yeah, but you've also got to determine whether the equator that you're looking at is where the equator is now, because it wouldn't have been. It would have been somewhere else, especially with the actual angle of the Earth's tilt changing. It's roughly 23.5 degrees now, but it's not always at that. It wobbles like a spin top.
That's exactly right. So again, that's delving back into the rock record and trying to use the alignment of mineral grains and how they align with Earth's magnetic field, but trying to couple that with precise dating is actually a very challenging task. It's already very difficult to date these old craters themselves because, as you can imagine, with these old pieces of continent, they've been around for such a long time, their surface gets eroded away. So you're really left with a very deep erosional level of the crust. So it's really great that we've been able to find this structure and get a precise date on it. I should say as well, there is evidence for older impact events, but not older craters. So we have things like spherical beds. So like that's airfall material has been trapped within rock record as well, and that does stretch back further in time. And of course, we also think about the late heavy bombardment, which constructed the Earth, which is much older. Again, there is evidence for older impact events, but they just haven't left a crater behind.
Yeah, they left the planet behind.
Yeah, exactly. That's the point, right? Yeah. So that we have to be careful about that.
That's Professor Chris Kirkland from Curtin University, and this is Space Time. I'm Stuart Gary. An analysis of a plume of gases and frozen sea spray ejected deep into space from the Saturnian ice moon Enceladus suggests its interior is far more complex than previously thought. The data, collected by NASA's Cassini spacecraft during its final close flyby of Enceladus in October 2015, found an abundance of carbon dioxide, best explained by geochemical reactions on the seafloor between the moon's rocky core and liquid water from its subsurface ocean. Now, integrating this new information with previous discoveries of silica and molecular hydrogen points to a more complex, geochemically diverse interior. The study's lead author, Christopher Glean from the Southwest Research Institute in San Antonio, Texas, says by understanding the composition of the plume, scientists can learn more about what the Enceladian ocean is like, how it got to be this way, and whether it provides an environment where life as we know it could survive. The new findings follow the development of a new technique for analysing mass spectrometry data of the plume composition to estimate the concentration of dissolved carbon dioxide in the ocean. This enabled modelling designed to probe deeper into interior processes. Based on the findings, Enceladus appears to demonstrate what could only be described as a massive carbon sequestration project. Of course, on Earth, climate scientists are exploring whether a similar process could be utilised to mitigate the industrial emissions of CO2, which are dramatically changing our climate. Using two different data sets, the authors derived carbon dioxide concentration ranges that are intriguingly similar from what would be expected from the dissolution and formation of certain mixtures of silicon and carbon-bearing minerals at the seafloor. Another phenomenon that contributes to this complexity is the likely presence of hydrothermal vents inside Enceladus. On Earth's ocean floor, especially around the mid-ocean ridges, we find hydrothermal vents emitting hot, energy-rich mineral-laden fluids. The nutrients provided by these black smokers allow unique ecosystems teeming with unusual creatures to survive. The dynamic interface of a complex core and seawater on Enceladus could potentially also create energy sources that might support life. While scientists haven't found any evidence for the presence of microbial life in the oceans of Enceladus, the growing evidence for chemical disequilibrium offers a tantalizing hint that habitable conditions could well exist beneath the moon's icy crust. Cassini detected molecular hydrogen as the spacecraft flew through the plume in 2015, and this followed the detection of silica particles during an earlier flyby. The two chemicals are considered markers for hydrothermal processes. The authors say distinct sources of observed carbon dioxide, silica and molecular hydrogen imply mineralogically and thermally diverse environments in a heterogeneous rocky core. It suggests that the core is composed of a carbonated upper layer and a serpentinized interior. On Earth, carbonates commonly occur in sedimentary rocks such as limestone, while serpentine minerals are usually formed from igneous seafloor rocks which are rich in magnesium and iron. This suggests that hydrothermal oxidation of reduced iron deep in the core creates molecular hydrogen, while hydrothermal activity intersecting quartz-bearing carbonated rocks produces the silica-rich fluids. Such rocks also have the potential to influence carbon dioxide chemistry in the ocean through low-temperature reactions involving silicates and carbonates at the seafloor. Glenn says the implications for possible life enabled by a heterogeneous core structure is intriguing. The model could explain how planetary differentiation and alteration processes create chemical energy gradients needed by subsurface life. You're listening to SpaceTime. Coming up next, the European Space Agency's Cheops satellite activates its science instrument, and later in the science report, discovery of a new species of the deadly meat-eating dinosaur, Allosaurus. All that and more still to come on SpaceTime. The European Space Agency has activated the primary science instrument aboard its Characterising Exoplanet Satellite, Cheops, to begin the mission's in-orbit commissioning phase. Cheops was launched aboard a Soyuz rocket from the Kourou Space Center in French Guiana on December the 18th. It was successfully deployed into a 700-kilometre high orbit. The probe's designed to determine the size of known extrasolar planets, or exoplanets, which will allow better estimates of their mass, density, composition, and how they're formed. The 300-kilogram spacecraft uses a high-precision photometer equipped with a 300mm aperture telescope attached to a charge-coupled device. The instrument began by running its first set of health checks to determine that its control units are operating as planned and that the expected thermal conditions can be reached. Mission managers also obtained their first dark image, an image produced without receiving any light from external sources, essential for a proper calibration of the instrument and to demonstrate that it is performing as expected. Further tests of the spacecraft and its instruments will continue over coming weeks. A key milestone has been the removal of the telescope cover, allowing the instrument to capture its first images of the sky. But that had been delayed by several days to allow some tests to be repeated. While everything is functioning as intended, the data analysis convinced Cheops mission managers that several instrumental parameters could be further optimized, resulting in the team repeating several tests. Cheops project scientist Kate Isaac says this mission is another step in the program to answer that ultimate question of humanity. Are we alone in the universe?
It's very exciting because what we'll be doing is following up on known exoplanets. More than 4,000 have been discovered to date in the 25 years since the first exoplanet orbiting a sun-like star was found. And Cheops provides us with an opportunity to do some first-step characterization. We'll be studying some of the smaller planets, so planets, so-called super-Earths, so Earth to Neptune-sized planets, and looking to understand better what they're made of and how they form and evolve. And this is one of the steps towards perhaps the ultimate question that we ask ourselves as a civilization, and that is, are we alone? It's been a really interesting project to work on, fast, unlike some of ESA's larger missions, which have much longer timescales. I've been involved from not quite the beginning, but from about 1.5 years since the mission started. And so what is really nice is I've been involved in the development, and I'll be working now on the operations. So we'll be starting to see the first results come through in a few months' time, making sure that the satellite survived the launch and that the instrument performs as we expect it to and we need it to. And then once we've established that everything works and works well, we'll be able to start doing the science. And that'll be very exciting, following up on some of the targets which have been shown to be very interesting by other missions, but Cheops will put the icing on the cake. The science program of Cheops is defined by the science team of Cheops, so from the consortium. 80% of the time goes to them, but 20% is open to the worldwide community at large. If you have a good proposal, you can apply for time, and if it's of high scientific merit and you make good use of the capabilities of Cheops, Cheops will give you time. Very exciting opportunity for scientists at large. What's my favorite exoplanet? That's an interesting question because you could say that the first exoplanet to be found, hot, puffy, gassy Jupiter-like planet, is a very interesting planet, but also the smaller planets, rocky, lava worlds. It's difficult. There's such a wide range of planets that have been discovered. All sorts of sizes, masses, temperatures, orbits, all very, very different from those in our solar system. It's a difficult choice. It's like opening a chocolate box and you asking me which is my favorite chocolate. I like all chocolate, milk chocolate, but choosing which one to go for first is a difficult one. So with Cheops, we use the technique of transit photometry, and that is to monitor the light from a star as the planet moves between the star and the observer. So here we have our star, our planet. What we do is monitor the light as the planet moves across the disk of the star. So what the planet does as it moves across the disk is to obscure part of the light from the star. The bigger the planet, the more light it obscures. So the smaller the planet, the less of the light that we block. And so the more difficult it is actually to measure the transit depth because it's smaller. And that's actually the benefit of Cheops. We'll be looking at these smaller planets, and because we'll be following up, we'll be able to come back to the star and its planets each time the transit occurs. We'll be able to observe all sorts of transits around the sky and come back at this critical period as the planet moves across the disk of the star. What we can also do is measure the so-called phase curve of a planet. And so what we're doing there is measuring the output of the light from the star as the planet moves the whole way around the orbit. So what we're doing there is measuring the reflected component of the light from the planet, as well as the dip caused by the obscuration of the star by the planet. And from this phase curve, we're able to find out quite a bit about the dynamics of the atmosphere.
That's Cheops project scientist Kate Isaac speaking to ESA TV. You're listening to Space Time. Coming up on the Science Report, researchers date the kingdom fungi to at least 800 million years, and how to make the perfect cup of espresso. All that and more still to come on Space Time. And time now to take a brief look at some of the other stories making news in science this week with the Science Report. Australian scientists have become the first in the world outside China to recreate the 2019 nCoV coronavirus in the laboratory. And unlike China, which is refusing to share the virus, the Australians will share the virus with other scientists globally in the hope that it may help efforts to diagnose and treat the disease. The outbreak has now killed hundreds of people and infected many thousands globally. It began with animal-to-human transmission through airborne respiratory droplets, but has now mutated to allow human-to-human transmission. Coronaviruses are a large family of virus causing illnesses ranging from the common cold to more severe diseases like Middle East respiratory syndrome MERS, which originated in Saudi Arabia, and severe acute respiratory syndrome SARS, which originated in Ganzhou in China and killed more than 800 people. Meanwhile, a new study claims this new coronavirus may well have come from snakes. A report in the journal Medical Virology claims an evolutionary analysis compared the genetic information from this virus with information already available from other viruses, finding that 2019 nCoV appears to have mutated from a combination of the coronavirus found in bats and another coronavirus found in snakes. The unique mix of proteins changed the shape of the receptors that allow the virus to bind onto and infect cells. Researchers say this recombination may have allowed cross-species transmission from snakes to humans. The study notes that the first patients infected with the virus were exposed to animals in the live animal meat markets in the Chinese city of Wuhan, where seafood, poultry, snakes, bats and other farm animals are sold. The largest ever genetic sequencing study of autism spectrum disorder has identified 102 genes associated with the risk of autism. The findings, reported in the journal Cell, helps towards teasing apart the genes associated with autism from those associated with intellectual disability and developmental delays, conditions which often overlap. Researchers collected and analysed more than 35,000 participant samples, including nearly 12,000 with autism, the largest autism sequencing cohort ever. They identified 102 genes associated with autism risk, 49 of which were also associated with developmental delays. The study shows autism genes impact brain development or brain function, and that both types of disruptions can result in autism. They also found that both major classes of nerve cells, excitory neurons, which trigger a positive and activating change in the downstream neural membrane upon firing, and inhibitory neurons, which trigger a negative change upon firing, can be affected in autism. Scientists have determined that the kingdom fungi, or is it fungi? Let's call it mushrooms, originated at least 800 million years ago. The evolution of fungus is very mysterious. Only around 2% of all the species thought to be in this kingdom have been identified, and their delicate nature means fossils are extremely rare and difficult to tell apart from other microorganisms. Until now, the oldest confirmed mushroom fossil was 460 million years old. Now, a report in the journal Science Advances describes the discovery of fossilized remains of mycelium, a network of interconnected microscopic strands in rocks in the Democratic Republic of Congo, dated to between 715 and 810 million years. This was a time in Earth's history when life was still very much in its infancy on land. Meanwhile, paleontologists have identified a new species of the deadly meat-eating dinosaur Allosaurus. A report in the journal Piaget claims these 9-metre 1.8-ton theropod remains were unearthed at the Dinosaur National Monument in northeastern Utah. The new species, Allosaurus gimadsini, is based on two spectacularly complete skeletons. The new species is distinguished by low crests running from above the eyes to the snout and a relatively narrow and flat back of the skull. These two-legged carnivores featured long forelimbs and sharp recurved claws, and a large head with 80 sharp teeth. Allosaurus jimetsini lived during the late Jurassic period, between 152 and 157 million years ago, when it was the top predator of its ecosystem, a semi-arid inland basin filled with floodplains, braided stream systems, lakes and seasonal mudflats. A team of mathematicians, physicists, materials experts, and even a couple of baristas have applied their combined brain power to one of the most pressing questions of our times. How do you make the perfect espresso? They brewed up a mathematical model taking into account the amounts of water and coffee needed, how finely ground the coffee should be, and what the water pressure should be in order to determine the effect on the end product. Most baristas use large amounts of coffee ground as finely as possible, but the team found that this actually clogs up the coffee bed, so many coffee grounds are never touched by the water and the results are inconsistent. They say the best espressos are achieved when they use less water or less coffee and ground the beans more coarsely, leading to the maximum yield and high levels of consistency between shots. You can read the findings in full in the journal Matter, perhaps while you're enjoying your favourite cup of joe. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through Apple Podcasts, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, from SpaceTimeWithStuartGary.com, or from your favourite podcast download provider. If you want more SpaceTime, check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web that I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram. On Facebook, just go to www.facebook.com/SpaceTimeWithStuartGary, and you can also find us on the Spacetime with Stuart Gary YouTube channel. Spacetime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to Spacetime with Stuart Gary. This has been another quality podcast production from Bytes.com.